everyone. My name is Tae-Kwan, a PhD student in KAIST. Today I'll be presenting our work named Granular Concept Circuits for the fine-grained circuit discovery for concept representations. This research was conducted in collaboration with co-first author Se-hyun Lee. Let me start with a simple example to introduce the motivation behind our work. Recently, many researchers in the interpretability communities have focused on explaining the circuits that drive specific decisions in large AI models. In the language domain, for instance, circuit analysis often extracts subgraphs that are responsible for each individual token. However, in the vision domain, most existing studies identify circuits that represent an entire class or a set of images rather than a circuit for a specific fine-grained concept. This is largely because visual models do not come with explicit concept-level labels. Yet, as shown in many prior studies, visual concepts in deep networks are not localized to a single neurons or layers, but they are represented in a distributed manner from low-level texture to high-level semantics. This leads to our key research question: where in a deep vision model is each specific circuit encoded? Various methods have been proposed to extract concept circuits in deep vision models. First, CRP distributes neuron relevance score across layers, showing how class-related information flows through specific channels. However, this method does not explicitly extract circuits. It simply traces the propagation of relevance scores, and it is limited to information tied to a particular class. Also, Visual Concept Connector, namely VCC, also focuses on class-related information, but explicitly constructs the circuits. It uses concept activation vectors as its base unit to form a circuit, which means it relies on derived representations rather than the model's actual internal components, which is a key limitation. The method most similar to ours is ADVC, which directly utilizes the model's native components to discover circuits. Unlike CRP or VCC, ADVC can identify circuits that represent not only class level, but also image set level relationships. However, it still tends to merge multiple fine-grained concept circuits within a class or dataset into a single unified circuit, making it difficult to capture detailed or concept-level structures. To address the limitation of previous approach, we propose a new visual circuit tracing method called Granular concept circuits. This method identifies fine-grained circuits that encode specific concepts related to one or more core image. For example, when a Maltese dog image is given as a query, our method can separately discover the circuits associated with the eyes concept or the fluffy tail concept within that image. Importantly, the discovered concepts are not restricted to the class level as long as they are conceptually relevant to the queries. Our method can capture them even if they are not directly tied to the labeled classes. To begin with, a well-formed visual concept circuit must exhibit meaningful connections among its components and consistently represent the common piece of information. Based on these two criteria, we introduced two corresponding score metrics to evaluate each circuit. To measure the first property, which is meaningful connections among its components, we use the neuron sensitivity scores. This score captures how strongly a neuron in layer L functionally depends on the neuron in the next layer L plus 1. Specifically, we mask out a target neuron in layer L by setting its activation to 0 and then observe how much the activation of neurons in the layer L plus 1 changed. In other words, it quantifies the influence of a source neuron on a target neuron using an intervention-based approach. If general masking the target neuron causes a large change in the source neuron's value, we interpret this as a strong functional dependency between the two. Second, we evaluate whether each circuit consistently represents a common piece of information. To do this, we introduce the semantic flow score, which measures whether two neurons share not only functional relationships but also semantic consistency within the same circuit. We infer the semantic meaning of each neuron by examining the images that most strongly activated. For each neuron, we collect the top 100 highly activated images and then measure the overlap between the image set of target neurons and its connected source neurons. This overlap quantifies how well the target node preserves the information flowing from the source. A higher overlap indicates a stronger and more meaningful semantic flow between neurons, suggesting that they jointly represent coherent information within the circuits. In part C of this figure, we illustrate examples of neurons analyzed using our two proposed metrics. The blue histogram at the bottom shows the overall distribution of each score, and we highlight three representative cases, shown in purple, green, and orange, which provide a clear intuition. So let's start with the purple one. So this case has low values for both scores, meaning it lacks both functional and semantic coherence. And also, the green neuron represents an interesting contrast. It shows a high neural sensitivity scores but a low semantic flow score. This means that although it is functionally connected to subsequent neurons, it does not carry semantically consistent information. When we visualize the activation, we can see that this neuron still fails to represent any concepts related to the query, the black node in the figure, indicating that high functional dependency alone is not enough for semantic alignment. Finally, the orange neuron achieves high scores on both metrics, and this is exactly the type of neurons we aim to capture. In this case, the neuron originally responded broadly to face of various animals, but through our analysis, it was refined into a circuit components that specifically represent dog faces. This demonstrates how our metric helps isolate fine-grained, meaningful concept circuits from broader and noisier feature groups. We then iteratively identify such high-scoring neurons and connecting them to construct the finer circuits. To initiate this process, we first select the top 500 highly activated neurons for each query and designated them as loop nodes. During circuit constructions, many of these loop nodes merge with nodes from earlier layers, meaning that the final number of distinct circuits is significantly smaller than the initial set of loop nodes. On the screen, you can see three sets of results displayed from top to bottom. Each of these corresponds to a different granular concept circuits extracted from the same query image. Although they are all come from a single image, each circuit represents a distinct feature concept, such as the flag, the sky background, and the clock within the scoreboard scene. These concepts are not directly tied to the class labels, but they are still visually and semantically presented in the image. This demonstrates our method's ability to disentangle and represent multiple query-related concepts within a single image. Note that, to the best of our knowledge, this is the first approach that successfully constructs circuits capturing fine-grained and diverse concepts within one single query. In these slides, we present the broad applicability of our granular concept circuit frameworks across different models, datasets, and layer depths. As you can see, our method performed consistently well across architectures range from LesNet to Vision transformers and datasets from ImageNet to Cube200. This demonstrates that GCC is not really limited to a specific model structure or domain, but rather provides a general and flexible ways to trace concept circuits in diverse visual backbones. We also evaluate GCC across different layers, from early convolution layers that capture low-level features like edges or colors, to deep layers that encode high-level semantics such as object parts or category-level concepts. We also conducted a user study with 33 participants to assess how well the circuit discovered by our method aligned with human perception. So participants were asked to evaluate the granular concept circuits based on three aspects: correlativeness, diversity, and prototypicality. As shown in this figure, the average score were 3.65, 4, and 4.45 out of 5, indicating that the extracted circuits are generally meaningful and well structured. The significantly lower score for query-relativeness suggests that our method sometimes indicates not only domain objects, but also contextual or background features capturing a broader concept scores. We further examined the perceived appropriateness of the node-to-node and query nodes connections in Figure D parts, where more than 90% of participants agreed that the discovered relationships were reasonable. And also, when compared to the VCC method, 70% of users preferred our method, noting that it reveals richer and even more diverse conceptual representations. Our method can be applied in a various of useful ways. The first application is auditing misclassified queries, understanding where and why the model made an error. Beyond error analysis, our method also excels at discovering shared concepts across different queries. These results highlight the ability of our framework to capture clear-transcending, high-level features that are often overlooked by conventional backward-based methods. So, in conclusion, so far we introduced granular concept circuits, a novel and effective method for discovering visual circuits that represent specific concepts related to given query. To construct these circuits, our method iteratively assesses interneuron connectivity, focusing on both functional dependencies and semantic alignments. By automatically discovering multiple concept circuits, our approach offers a profound concept-wise interpretation of models and is the first to identify circuits tied to specific visual concepts at a fine grain level. So this is the end of presentation, and thank you.